Welcome back. Let's do an example. Let's say we have this double integral of some function f of xy over the plane region R, where R is this region with four sides here, and the equation for each of these sides is given. So this side is the straight line x minus y equal to 0. This side is the straight line given by the equation x plus y equal to 2. This side is x plus y is equal to 0, and this side is x minus y is equal to 2. Okay, so we are integrating f over this region, and let's say that we do the following change of variables. So let's say we substitute x and y with t of uv, where t of uv is u plus v comma u minus v. In other words, we are substituting x with u plus v, and we are substituting y with u minus v. Now, if we make this change of variables, then the new integrand will have two factors, where the first factor is obtained by simply substituting x and y with u plus v and u minus v respectively in the original integrand, and then we're going to have this extra factor which we will compute in a second, and then we also need to figure out what is the new region of integration. Now, to figure out the new region of integration, we need to figure out the inverse of t. So x is u plus v and y is u minus v. To figure out the inverse of t, we need to solve for u and v in terms of x and y. So u would be, so from these two equations, if we solve for u, we are going to get u is x plus y divided by 2, and then v would be x minus y divided by 2. So uv is the inverse of t evaluated at xy, which is x plus y over 2 comma x minus y over 2. So recall that the new region of integration d would basically be equal to the inverse of t applied to the original region of integration R. So what is d then? Well, notice that, so we got that u is x plus y over 2 and v is x minus y over 2. So notice that the blue side here, x minus y equal to 0, that side will be mapped onto v equal to 0. So if x minus y is 0, then v is 0. So this blue side is mapped into mapped into the line given by v is equal to 0 in the uv plane. So in the uv plane, that's just the u-axis. The purple line here is given by x plus y is equal to 2. Now, if x plus y is 2, then u is 1. So we see that the purple line is mapped onto the purple line in the uv plane, which is the vertical line at u equal to 1. Similarly, the green line segment here, the green side here, green side of R is given by x minus y over 2, and x minus y is 2, then v is 1. So the green side is given by the line v is equal to 1 in the uv plane, and lastly the orange line here is mapped onto the orange line here where u is 0. So T inverse maps R onto D. So D is the new plane, new region of integration. So we get that the double integral of f of xy over R is equal to the double integral of f of u plus v comma u minus v over d. And then we have this extra factor in the integrand that we still have to figure out. So this is, recall that the absolute value of the Jacobian, and the Jacobian is denoted by this symbol, and it is given by this 2 by 2 determinant. So where the first row, the entries in the first row are partials of x with respect to u and v, and the second, the entries in the second row are partials of y with respect to u and v. Now, recall that x is u plus v, so the partial of x with respect to u is 1, the partial of x with respect to v is 1. The partial of y with respect to u is 1, the partial of y with respect to v is -1. So if we plug those in, we get the 2 by 2 determinant 1, 1, 1, -1, and the determinant is -2. So that's what's going to go. In this second factor right here. So again, we're taking the absolute value of that. So that means this factor here, extra factor here, would be 2 in this case. Okay, so that's so in the previous video, that's what I said, that the extra factor here would be given by this Jacobian, but actually it's the absolute value of the Jacobian. Okay, so basically then let me recap the change of variables formula for the for double integrals. So let's say that we change variables from xy to uv via some function t, where t is invertible. That is, we are substituting x with some function of uv and y with some function y of uv. Then the Jacobian of this t is denoted by this symbol here, delta xy over delta uv. And so this is the way I read it, is the Jacobian of xy with respect to u and v. And this is the determinant of the 2 by 2 matrix, where the entries in the first row are partials of x with respect to u and v, and the entries in the second row are partials of y with respect to u and v. Okay, so that's the Jacobian of the transformation or the mapping T. So now so now I want to state the change of variables formula for double integrals. So assuming that T here satisfies 4 conditions, where the first one is the T is C1. So this means that the partials of x and y are continuous. Second condition is that the Jacobian of t is not the zero function. And the third condition is that t maps d onto r. And the fourth condition is that t is one-to-one on d, except possibly on the boundary of d. Under these 4 conditions, then the double integral of f of xy over the region R is equal to the double integral of f of x of uv comma y of uv multiplied by the absolute value of the Jacobian over the plane region D. And this integral is with respect to u and v. That is, if we are substituting xy with u and v via the mapping T or transformation T, then the new integrand would be given by this, and the new region of integration D is given by the inverse of T applied to R. Now, we're not going to prove this theorem because this is kind of outside of the scope of this course. We will, however, justify this in the case of one specific substitution in the next few videos, and that substitution is the polar substitution. And so we are going to focus on the polar substitution in the next video.